this is kind of your blueprint, if you will, for all of our chemical reactions. What we'll go through and do is look at each of these in kind of some detail, and we'll address what you need to know within that classification type. Okay? When we go through and look at these, we'll kind of address some stuff right now. Okay? The combination and the decomposition reactions, these are purely recognition. So what do I mean by that? Did you recognize that was a decomposition reaction? Did you recognize that was a combination reaction? That's it. All right? So you're given the whole thing, reactants and products. All I want you to be able to do is look at it, recognize that it was a combination or a decomposition. You could be asked after that to balance the equation. That's a secondary aspect of this. Right? That would be kind of the next layer of difficulty on top. Okay? But where it starts with our chemical reactions is first, what are they? The first two, you just have to be able to recognize that they exist. Okay? That they are combinations and decompositions. Does that make sense? All right. Single replacement, double replacement, and neutralizations are all an extra layer. All of those require that you be able to predict products. Right? So that means beyond just the recognition, looking at those and saying, well, that is a single replacement or a double replacement, you could be given, for a single replacement, just that. Right? And in fact, we could take this a step further. You could be given that. By looking at that, you need to be able to identify that that is a single replacement reaction. And you need to be able to identify that the products coming out of that would be these. Okay? So it is an extra piece of information for that. You have to do the same thing for the double replacement. Okay? You have to be able to look at just reactants and say that is a double replacement reaction. And because I know it's a double replacement, I can now predict that the products are these. Extra little nasty tidbit on both of these. Okay? It's a little bit less challenging in the single replacement. You will also have to specify phases. Okay? All of that information is stuff that you're given on the test on how to decide what the phase is. Okay? So it's an extra piece of information. For the single replacements, it's known as an activity series. Okay? Which if you've been reading ahead, you should have read about. For the double replacements, it's a solubility table. Okay? So you're required to interpret that extra information. It is stuff that's given to you on the test. If you take a look at your first exam, there should be two little sections with boxes around them. One says activity series, one says solubility rules. They're already given to you. Okay? Those may change depending on what question I ask on the exam. Okay? But I'm not going to ask a question on the exam where you don't have that information. On your semester exams, the final exam is a little bit different. Okay? Neutralization you will also have to go through and predict. But you should have already known that you have to predict the neutralization. Why is that? What kind of reaction is a neutralization?
Acid.
It's a double replacement. Do you have to predict the double replacement?
Mm-hmm.
Yeah. So if a neutralization is a double replacement, then what do you got to do? You also got to predict it. Okay? The one kind of extra thing that comes out of the neutralization, which could be argued as more difficult, is that when we go through and specify our phases, so I heard someone shout out acid, so we know there's an AQ in there for that first one. Okay? You're always given the reactants, so those will show up as aqueous. When we typically look at a neutralization, what is the phase of BA? Anybody read that far ahead? No? Okay, well, cool. So that's why no one answered. That explains it. Okay? That product is typically, when we're looking at a neutralization, aqueous. What is the phase for HOH? Okay. That one should not really be a challenge, but that's an extra one. You're not expected to be able to predict liquid phases. You're really only expected to be able to predict aqueous and solids. Okay, the liquid phase becomes much more difficult to predict. Why do we expect you to predict it then, if it's that much more difficult? Sort of. Why do we expect you to predict that HOH is the liquid phase?
Because there'll always be liquid phase.
What is HOH? Water. And as we can clearly see from today, from the sky, what phase is water? A liquid. That's why we expect you to memorize it. Okay? You've had enough experience with water to recognize the phase as liquid. That's why you need to know it. Okay? Virtually all other liquid phases you can ignore. Okay? That will be specified to you. Okay? Kind of, sort of? Okay. So when we go through and look at our combinations, this slide gets dicey because what did I just say about our combination reactions? What do you have to do? You just have to recognize them. You don't have to predict anything, you just recognize them. And yet, what's happening on this very next slide? Magnesium metal reacts with oxygen gas to produce. What am I asking you to do? Predict the product. Why am I allowed to ask you to predict the product now? Are you given more information, like the reaction of a metal with oxygen? Yeah. Okay. When we react a metal with oxygen, we just do a combination of those two. Okay. So given that extra piece of information, I know that magnesium, metal, being what phase? Solid. Reacts with oxygen. What phase? Gas. Is that the proper symbol for oxygen gas? No. Okay. And if we remember that stupid mnemonic, it's the of part. Okay. Have no fear of. It's a diatomic element. To produce, now it's a combination. I've combined magnesium with oxygen. Okay. In the prediction of our products, we have to make sure our product is actually valid. How do we make sure our product is actually valid? We have to balance the charges. Remember that nomenclature section? Okay. I don't care that you know how to name that compound. I do care that you recognize how to balance out those charges. What is the charge on magnesium? A +2. What is the charge on oxygen? -2. Is that formula correct? Yes. Do I know anything about the phase? No. I don't expect you to predict that. So that's all you would get for that product. The next layer, balance the whole equation. Is the equation balanced? No. Magnesium, there's only 1 on each side. Oxygen, there's 2 on the reactant. There's 1 on the product. How do I fix that? I put a 2 in front. Now my oxygen is balanced, but the magnesium isn't. So what do I need? I need a 2 in front of that magnesium. Notice, how much of the work did I show for balancing here? 0, none. Why? Okay. I thought it was easy. At least one other person in this classroom thought it was easy too. If you don't think it's easy, what should you do? Show all that work. Okay. I would argue on the test you should show your work regardless, so that way you can go back and check your work to verify your answer was correct or not. Does that make sense? Okay. What happens if we change it up? Come on. Okay, it's not connecting.
Mine called, I just got a text.
I've got an alert. The class started. Yes, I know I've run out of disk space. Let's try again. And the computer is actually locked up.
I don't think the highlight, it'll take you like 40
Sulfur solid reacts with oxygen gas to produce sulfur dioxide. Can I do the first rule, the reaction of a metal with oxygen? No, why not? Sulfur's not a metal. So how would I be able to go through and do this one? Okay, I could use rule 2. Do I need to use rule 2 to do this one? Let's start to write out what the sentence says. Sulfur solid, so S, S. That could be bad. Oxygen gas, O2, G. To produce, SO2. Do I have a phase? Did I specify a phase? Does anybody know the phase of sulfur dioxide? I heard some people make statements. Do you know that, or are you guessing and hoping you're 33% right? You're guessing. Okay, so stop guessing. No, you don't know. So we don't know the phase. How is this one different than we did for the red one? I actually told you the product. Why did I tell you the product? Let's try and use the same rules that we used for the last one. Okay? For the last one, what happened? We did this. ... question mark. Predict the product. And don't tell me SO2. Well, I mean, you could, but you need to give me a reason why. Okay? Sulfur with oxygen. Awesome. I like that. I need to make sure that those balance, right? What's the charge on sulfur?
Minus 2.
When is sulfur a -2? When it is an ion. How do we know we have an ion? Those of you being like, this sounds like a trick question. It was. How do you know you have an ion? And no.
No. Because the charge is specified.
Nope.
We don't have a specified charge.
We'll get to that.
Not yet, at least.
Because it's combining with?
When do you have an ion? What'd you say? When you have a metal and a nonmetal, because you have an ionic bond. Is sulfur a metal? Is oxygen a metal?
No.
Do you have an ionic bond?
No.
Do you know the charge on sulfur? No. The charge on sulfur only applies to ionic compounds. That's not ionic. Can we predict the product? No, we don't know what the charge is on sulfur, so we literally cannot predict the product. So how do I, as an instructor, fix that? I tell you that the compound is sulfur dioxide. Okay? We have to be aware of those subtle changes in the system. Okay? That's not explicitly stated in the textbook, which is why when we talked about combination reactions, I don't talk about predicting them necessarily. The biggest issue with our combinations is to do what? Nope. What's our biggest deal with our combination reactions? What do I expect you to do? Recognize that it's a combination reaction. That's it. Okay? So you need to be given that statement, and you have to look at it and say, that's a combination reaction. When you read the English, and this could be a little bit weird, do you recognize those blue words mean combination reaction? Okay? Some people might say yes. More than likely what's happening is they recognize this to produce, and they noticed what? Okay? We could say 2 words. If there's 2 words, what does that tend to mean to you? Separated, so 2 products. If there's 2 products, is it a combination? No. So when they looked at to produce, what did they see? Not that there's 2 words. They saw 1 compound. And really what they probably saw, or the most important thing, is actually what they did not see. What did they not see? An and. Because there's no and, how many products did I make? 1. 1 product means, oops, sorry. Which of my reactions produce only 1 product? Combination. So they were able to recognize it from the English. If you can't recognize it from the English, what should you do?
Take another English class?
That's a bit over the top. Convert the English into chemistry and write it out as the chemistry language that matches the format we've got. Kind of make sense? Hi. You want to do some nomenclature? Yeah? Okay. I'll give you 4 minutes again. Okay, so we'll start addressing some things. We've got them all listed up there. Notice for that very first one, we've got cadmium, which is a metal, so I know it's ionic. Notice I circled Cn and pointed to the ternary. Cn is more than one element, so I'm looking at a ternary compound, so we're going to have to name this according to the ternary ionic rules. Okay. The second one is covalent. We just jump straight to the name. The Greek prefixes tell us the number of each. Chromium 3 oxide, I did not actually finish this one, so we'll talk about that one. But I've circled the D in reference to binary. Okay. That is kind of a dangerous thing to do, as we'll see in a... Actually, we can reference it right now. Okay. Typically, if you see a D, it's a binary compound. Okay. With 2 exceptions. What are those 2 exceptions? Okay. What is the name of SO4 minus 2? Sulfate with a T. Okay. SO3 minus 2. Sulfite with a T. What are the other? NO3 minus. Nitrate with a T. Okay. OH minus. Hydrox. Ide with a D. So we'd think binary, it's an exception. OH is 2 elements. It's actually a ternary. What's the other exception? Cyanide. Okay, is also an exception. Okay. If you see T at the end of your name, that's immediately a red flag that it's a ternary ionic compound. Okay. If you see D in that ending, it's probably binary. Those 2 exceptions you have to memorize. Okay. Those are going, oh, there's more stuff to memorize. I already told you to memorize that hydroxide and cyanide have those names. Okay. That was already on your list of things to memorize for your complex ions. Okay. So binary, because I see the D, I'm looking at chromium and oxygen. Last one's just a covalent compound. Again, the Greek prefixes specify out. Okay. If we go up to the very top one, I noticed at least one person wrote cadmium 2 cyanide. What is the charge on the cadmium? +2. So is that wrong? Yes. Okay, let's change the question. Is that correct information? Yes. Is that name wrong? Yes. Okay, the example that I would use is when you call out my name, you don't say Mr. Michael McFavlin. Okay. Granted, you wouldn't lose points for saying that, so it's not horribly wrong. Okay, but you'd probably get a weird look from me, and probably most of your classmates would be like, what are you doing? That doesn't make any sense. Okay? And instead, you would just call Mike. That extra information is correct, but according to the conventions of our system, it's too much. Okay? And we're adding unnecessary information. Unnecessary information is now defined as wrong, unfortunately. So how do we know cadmium is always a +2? You have to memorize it. Okay? I've been hearing this float around the tutoring center. Cadmium is a transition metal. I said, well, if it's a transition metal, you have to specify the charge. No. If it is a transition metal, usually you have to specify the charge, except for zinc, cadmium, and silver. Okay? So there's a reason why I didn't mention transition metals usually get a charge, because what happens when you interpret that is that it's not usually anymore and it becomes always. Okay? So be careful when you hear rules, because those exceptions can sometimes bite you. This would be a case. Make sense? All right. When we get all the way down to the chromium oxide, this one becomes a little bit more challenging to go through and deliver. So I'll write it out. This is how I go through and approach it. Okay, +3 and -2. And of course I didn't give enough space to do this, but we're going to do it this way anyway. Okay, X and Y, when I add those up, this has to equal 0, our overall charge. I get 3x minus 2y equals 0. Okay, as presented in past lectures, what we would do is guess. Okay, so I'm going to guess. That says guess. X equals, let's not guess the correct answer right away. X equals 1. I get 3 minus 2y equals 0. I would get y equals 3 over 2. I did that algebra kind of fast. If that bothers you, talk to me after class. Is that a whole number? No. Because that is a whole number, what does that mean about my guess? Okay, this is wrong. Okay, so we could go through and say capital F failure. This is where my colleagues have convinced me that I should soften that. It's a lowercase failure because I recognize it failed, and what do I now need to do? I need to guess again. So I will guess again. I'm going to guess the correct one. That says guess again. X equals 2. I would get 6 minus 2y equals 0. I would get y equals 6 over 2, which equals 3. Is that a whole number?
Yes.
Yes. Okay, I solved correctly now. The x equaling 2 corresponded to what? The amount of chromium ions, so there's 2 chromiums. The y was the S3, which corresponded to the amount of oxygen. And I now have my formula. Okay? Simplifications. Okay, there's one simplification I will go through and actually discuss. Okay, because I'm not doing the crossover method. Okay? When we write out this work, right, we've got our charges written underneath. The whole point is we need to find how 3 and 2 can equal each other. So what is the lowest common multiple for 3 and 2? 6. How do I make 3 a 6? I multiply by 2. What's the coefficient or the subscript for chromium? 2. How do I make a 2 a 6? Times 3. Okay? For those of you that want to call out the crossover, let's go ahead and real quickly look at titanium 4 oxide. Titanium oxide. What was the charge on titanium? A plus 4. The charge on the oxide? Minus 2. Guaranteed one of your answers is this. Crossover! Wrong. Okay, why is it wrong?
Because 4 is the lowest common.
The lowest common multiple between 4 and 2 is 4. How do I make the 4 into a 4? I multiply by 1. The coefficient with the titanium is 1. How do I make the 2 into a 4? Multiply by 2. Okay? If you decide to use the crossover, okay, that method still works-ish. I did it backwards, sorry. Right? 2, 4. You have to evaluate your formula. Is that the lowest common multiple or lowest common system there? No, I could reduce that because I could divide both by 2. So you can still do the crossover as long as you always acknowledge you have to check, did you pick the lowest common system? Okay. If you didn't, just reduce it down and you'd get the correct answer. Make sense? Okay. Questions about anything that's up there? How are you guys doing with nomenclature?
Yeah.
Deep sigh. Deep sigh is a good thing or a bad thing?
It's taking forever.
It's taking forever. That nomenclature packet as part of lab last week, or depending on which week you're in. Okay.
No.
If you go through and honestly attempt that all the way through, you should be good. Okay? You should be at least a B level as far as naming goes, if not higher. If you go through and kind of cheat your way through it and find answers online, because they're freaking out there, or just copy them from somebody else, all you're going to do is shoot yourself in the foot in 2 ways. Okay, 1, you're not going to get any nomenclature questions right on the exam, so your exam grade suffers. 2, depending on your lecture or your lab instructor, there may be a quiz. If there's a quiz on it, that's individual. If you've only learned how to do nomenclature by looking up the answer, you're going to fail the quiz. Okay? So go through and do the lab as best you can. If you want that lab practice, send me an email, because I don't think I've gotten that email yet from those of you that wanted that practice. Okay, and I can send that out to you. Okay, so let's take a look. Bunch of equations. See what you can come up with now. All right. Determine the reaction type and predict the product. Balance the reaction. Do as much as you can. If you can't figure it out, that's okay. We'll just stall at that point. So, first thing you're supposed to do for all of these, recognize. You need to be able to recognize the reaction type. What's the first one? The first one is a combustion. That other C word, not combination. Okay. The next one. Combination. Next one. That says decomposition. Next one. I'm just going to write DR for double replacement. Next one. Next one. Last one. Single replacement. Okay. Predict the product and balance the reaction. Do you have to predict the product for the first one, combustion? No, why not? It was already given to you. So you do have to go through and balance that one. So we'll set up the work right underneath it. So I'll temporarily erase that. So when we go through and set this up, carbon, left and right, what do we have? 4 and 1. What do we need to do? 4. What's the next one I balance? Hydrogen, left. Right. 2. What do I need to do? Put a 5 in front. Oxygen, left. 2, right. There's 2, but 4 of those, which means 8. And then there's 1, but 5 of those, which means 13. Can I make 2 equal to 13? No. Okay.
U times 13 by 2 and 2 times 13.
Okay, so what we could go through and do, and this is where we run into a variety of different methods behind this. I was trained that I would put 13 over 2. Okay. Does that equal 13? Oxygen's on the left. If I take 13 halves times O2, how many oxygens would I have? Well, I would have 13. Well, that would balance. What's the problem with writing that half in there? Okay, it's not a whole number. Okay, what we're looking at so far when we look at our equations is molecules. Can I have half of a molecule? No. So 13 halves doesn't make sense. Okay? So what I can now do is, well, I need to get rid of that half. How would I get rid of the 2? Multiply it by 2. So if I multiply 13 halves by 2, what do I have to do by the first one? Multiply that by 2. Multiply that by 2. Multiply that by 2. Okay? As far as there being easier ways, I've tried to look at a variety of ways, and nothing really seems to stick with me as necessarily being easier, per se. Okay? I heard someone suggest something that's potentially easier, is recognizing 2 and 13 and saying, what's the lowest common multiple between those two? 26. Which means I need 26 oxygens. How could I get 26 oxygens? That's going to become kind of hard on the right-hand side of the equation, because where does oxygen show up? 2 different places. So when I make the right-hand side 26, that's going to scaffold everything a little bit weird. Okay? The other option is just going through and saying, okay, when I go through and look at this system, or this equation, it didn't balance. It is impossible for me to go through and balance out the 13 and the 2. So I'm just going to multiply everything through by a factor. what factor should I multiply everything through by? As a hint, we literally just had it written up there. 2. Why should we pick 2? The part that's missing, the part that wasn't balanced, has a subscript of 2. What if it was a subscript of 3? Multiply everything through by 3. Okay? What does that do for our question or our equation? This now becomes a 2. What does the 4 become? 8. What does the 5 become? 10. Now I can go through and do the whole balancing process again and rearrange those letters. How many carbons? 8 and 8 hydrogens. 20 and 20. I don't know why I wrote 4. Thank you. 8 oxygens. 2 and 8 and the 2 gets me 16. 10 and the 1 gets me 10. 26. How do I make 2 a 26? Multiply by 13. Wait, isn't the answer I just had? Yeah, they're both doing the same thing. Okay. Your combustion reactions are the ones that notoriously do this, okay, and make it a little bit more challenging. Not all combustion reactions will encounter this, and it's not always combustion reactions that do it. Okay? But this process can occur. It occurs very rarely in Chem 130. It occurs much more frequently in Chem 151 because they're trying to mess with you. Okay? And understandably so. We're trying to make sure you know how to balance all those pieces. Okay? Kind of make sense? Okay, or at least enough that you can accept it. Okay. Next reaction, lithium metal reacts with bromine gas to produce. Okay, so we could be like, start to get in the groove of just writing things out. Lithium metal, solid, plus bromine gas. Saw a bunch of people write this down. It has to be Br2. That's the beer part of have no fear of ice cold beer. Bromine is a diatomic. It must show up as the 2. We could also do it as the 7. The 7 just never sticks for me. Everybody seems to like the 7 a little bit better, but it's one of those 7 that you have to memorize. Okay? What kind of reaction was this? Combination. I saw a bunch of people starting to draw products. Okay? And that was cool because they actually predicted proper products. What are you required to do for a combination? Recognize it. Are you required to predict products? No. So arguably, what should you do? Stop right now. You're done. Okay? There's no need to continue to predict those products. The only reason we were able to predict those products is because you were given extra information on the previous sequence of slides. So when we first saw that, you had more information to be able to answer that question. Okay? Here, we're not given that more information. Don't do it. Next one. Okay? We could again go through the process of practicing our nomenclature. We have sodium, hydrogen, carbonate. Okay? Didn't specify the phase. Then decomposes. What kind of reaction is this? Decomposition. Are you expected to predict products? No. So cool. You'd be done. Say that again?
When you do the carbonate, and we have that memorized, but you don't put the charge on it. Why?
Okay, so let's deal with the charges on that. I was kind of waiting to see if somebody would specify anything there. When we're dealing with our nomenclature, we do have to make sure that the structure we drew was correct. Okay? What is the formula for carbonate? CO3, 2 negative. What is the charge on hydrogen? A +1. What is the charge on sodium? +1. Is this formula correct? Okay.
Just out of pure curiosity, what is the actual decomposition of that?
We'll see it actually on the next slide. I believe that decomposition gets you sodium carbonate and H2O. I think that's right. Is sodium carbonate balanced?
That gives you three separate.
I didn't say the equation was balanced.
No, I'm saying that it gives you three separate.
And this is part of the thing. I don't have it memorized. I don't expect you to know what the products are. That's why we can jump for the next slide. We'll see it show up there. Next one is a double replacement. What do you expect it to do with a double replacement? Okay. Sodium chloride, NaCl, aqueous plus lithium nitrate, aqueous. What's the charge on sodium? Charge on chloride? Is that formula correct? Yes. Charge on lithium? +1. Nitrate? Is that formula correct? Yes. This would go through to produce products. Am I required to predict the products in a double replacement? Yes. So now you have to go through and do the exchange. We're exchanging the similar things. It's up to you which you want to specify as the similar things. I would make the argument that we should look at sodium and lithium as the similar things. Okay, why? They're both metals and
And the same group, too.
they're both in front. They're the first one I encounter, so I'm going to exchange the metals. I could just as easily exchange the chloride with the nitrate, okay, but for me it's easier to exchange the metals, so I'm going to end up with, because I'm exchanging the metals, I'm going to say LiCl, and the other one will be NaNO3. Do I have to check charges?
Wait.
Yes, I have to check charges and make sure the charge is balanced. They will. Am I required to specify phases? Yes. Double replacements were expected to do that. Have we talked about that yet in lecture? No. So you may not be able to do that quite yet. There's a hand.
For when you give us like on the test like combustion or combination
Uh-huh.
decomposition, do we have to? Can we just write the reaction, or do we have to like go through?
So what I believe you're asking is on the test, what I asked you to provide the equation lithium metal reacts with bromine gas to produce and expect you to provide the full equation. No.
So we just write combination.
Yeah, and I would change the question to get at what I would want. Okay. So where that could show up is identify the type of reactions. So, and if you take a look at the practice exam, there is a question with I think 5 or 6 different things saying, tell me what equation it is, what reaction it is. Lithium metal reacts with bromine gas to produce, question mark. You've got enough information to tell me it's a combination. So I would expect you to tell me combination. I don't expect you to do anything else with it. Okay? Yeah.
Is it wrong if it's reversed order if you put sodium nitrate first?
If you-
plus lithium?
If you do sodium nitrate first plus lithium chloride, no, it's fine. Okay? Addition is not additive. Communicative. Okay? 1 plus 3 is the same thing as 3 plus 1. So the order doesn't matter there. Okay? How would we specify those phases? In theory, it was in the, I don't remember if it actually showed up in the reaction video. In theory, it was mentioned there. Okay? And we also mentioned it earlier in class. It is aqueous, but why would you know that? How do you know those phases? Because, ooh, someone might have been saying it. No. Solubility rules. There's a list of solubility rules. You have to apply the solubility rules. Okay? If you don't know the solubility rules, you can't answer that. That's why when you look at your exam, what do you find on the front of the exam? A list of solubility rules. Okay? So don't stress about predicting those phases yet. Why not? They aren't provided here. We don't have the solubility rules, so we can't predict those yet. Okay? The next reaction is a single replacement. Are you expected to predict single replacement reactions? Yes. Okay, because I way overcrowded this slide. Okay, we need to exchange the most similar things. Zinc is a metal. What's the most similar thing in lead sulfate? Lead. Why lead? Lead is also a metal. So what happens? They exchange the locations. We get Pb by itself, and then zinc sulfate. Okay? I'm predicting a product. Lead by itself has no charge. What happens with the zinc sulfate? The charge is up there and kind of irritating. Are you required to know the charge on zinc? Yes, you're required to know it is a +2. What's the charge on sulfate? A -2. Is that product correct? Yes. Okay. Phases become a little bit more questionable here. We'll talk about those when we talk about our single replacements, just like with our double replacements. The next one down, we said was a combination. This one you should be able to go all the way through on. Why? I give you the product, so you should be able to not only predict the reaction type, but write the products and balance the reaction. All right, last one, single replacement, which means you have to be able to predict the products. Gold is a metal, copper is a metal, sulfur, non-metal, oxygen, non-metal. Okay, so what do I exchange? The gold and the copper. Okay, this is a fun one, so let's go ahead and draw this one out, because this gets at Carlos, right?
Yes.
Yeah, at a question that Carlo asked earlier in the class period. Yes, sorry, lost track of where I was. Gold and sulfate. What is the charge on sulfate? What is the charge on gold?
At least you're honest with it.
+1?
Yeah.
That is not one of the ones you're asked to memorize, which means, why are you not asked to memorize it?
Because it changes.
It changes. If it changes, can you predict what that formula accurately is? No. Okay. This shows up in the lab with the activity series lab, and it shows up in your homework, okay, or any kind of questions from the textbook. Same kind of thing is happening up on the board. Okay. When you encounter a question like this, okay, and this is a horrible thing to do because it's not always true, make the assumption that that species is a +2. Okay? Why? Because we got nothing else. We just predict it. Okay? Would I ever ask that on the exam? No. I'm aware of that issue. I don't want you just making bold-faced assumptions. Okay? So I will make sure to carefully select the metals that exchange so that you are expected to know the charge. Kind of like for that first single replacement we looked at with the lead and the zinc. Make sense? Okay. When you work questions again in the textbook, you'll get a question like that bottom one and it'll be like, well, how would I know? Okay? Kind of make sense? Okay. Decomposition reactions. Okay. There are patterns that follow for our decomposition reactions. Again, at this point, this is just kind of practice behind it. I don't think it's really necessary to go through a bunch of these. Okay. And I think I actually have these up here. Some of them are kind of interesting. So here's the one. Oh, it does get 3 things. Dang it. So I was wrong. Metal hydrogen carbonates decompose to give a metal carbonate, water, and carbon dioxide. So that sodium hydrogen carbonate question that I started to write out and then was challenged that I was wrong. And thank you for pointing out my failures. You know, it's always good. We got to stay humble. Yeah. Does that make you feel better? Like I'm wrong. See? Sodium hydrogen carbonate decomposes to form what? Okay, well, it fits the rule that we're given. Metal, hydrogen carbonate. Sodium is metal. H is hydrogen. CO3 is carbonate. Fits our pattern. What does it decompose to give? Metal carbonate, not metal and carbonate. There's not a comma. It's a metal carbonate. What was our metal? Sodium. Carbonate is CO3. Water. And CO2. Okay. Are you expected to be able to predict the balancing of CO2? What is the charge on carbon? Okay. Looking to the periodic table is not a horrible idea. What are you looking at when you look for carbon to figure out its charge?
How far away it is from the gas?
No.
It's -2.
No.
The change.
At best, you should recognize by looking at the periodic table it's not one you're required to memorize. Okay? Or sorry, at worst you should memorize that or recognize that. At best, what should you recognize?
The charge on the oxygen.
I'm still looking at carbon.
No.
There's kind of this bold line on the periodic table. What did that bold line mean? The differentiations between metals and nonmetals. Where's carbon? It's a nonmetal. Should I be looking for its ionic charge? No, because it's not an ionic compound. It's a covalent compound. I do expect you to be able to predict that there's 1 carbon and 2 oxygens. Why? Based off of the name of the compound, carbon dioxide. Okay? And yes, that can be confusing. We're looking at different rules for different reasons, and we have to be very careful with associating those. This is where practice comes into play. Okay? How do you know H2O for water? You just memorized that. Cool. That was your old knowledge. You just got to use it. Okay? How about metal carbonate? Did we provide the metal carbonate correctly? Is that one we're required to look at and actually balance those species out on? Where is Na? That's sodium. Sodium. Metal. If it is a metal, what do we have? An ionic compound, which means I have to balance the charges. What is the charge on sodium? +1. Charge on carbonate? -2. Are those charges balanced? No. What is the lowest common multiple between 1 and 2? 2, which means, how do I make the 1 a 2? Times by 2. How do I make the 2 a 2?
Leave it alone.
Multiply it by 1. There's my correct formula. Okay? Phases in this, just to be extra irritating. Why not? I do not expect you to predict the phase, at least yet, for sodium hydrogen carbonate, but water, liquid, CO2, gas. Good. Okay. We could also look at other ones. I don't care because I don't expect you to do it. Single replacements. Okay. Single replacements add an extra layer because you are now required to predict the products. And not only are you required to predict the products, you're supposed to be able to look at that and say that reaction does indeed happen. Okay? Which tends to be confusing. You're like, but if I did the shift, okay, and this is where you can ignore the words right there. Let's just ignore those. Okay? What would I predict for my products? PB plus ZnSO4. I will accept that. Most chemists freak out at that because it is not PB. What is that? Lead. I'm not looking at peanut butter. That's lead. It's not ZnSO4. It's zinc sulfate. Okay? So, in that prediction, have I done a good job? Well, I have to look at charges. What is the Zn? I did it. Zinc, it's a +2. Sulfate, -2. Did I predict the product correctly? Yeah, so I could go through and check the equation. Conveniently, I picked one. It is balanced.
And
Right.
if you're going the other way, then we'd be not sure.
What?
So say if it was going from
Zinc sulfate plus lead.
going
The other one?
Because isn't it +4 or +2 for that?
Oh, I see what you're saying, yeah. If we'd flipped this equation, how would we predict the formula for lead sulfate? We wouldn't, because we aren't required to know the charge on lead. Okay, so I conveniently picked an equation, and if you look at the text equation, okay, and you try and do the text equation that's up there, you'll notice it's a different one, because I screwed up the first time I built this. Okay, but if you go through and do that one, you'll find it's one you can't predict the charges on. You don't know those. So I made the adjustment with a new question, but then didn't fix the text. Okay? So the next question that comes up is, does the reaction happen? Well, when you look at this, would you think the reaction happens? Yeah, why? Because I drew something for the products, right? Like, if it didn't happen, why did I draw all that? Okay? How many of you are like, know what you would do if you won $1 million?
Yeah.
First thing,
Okay? How do you know if you won $1 million? Like, why are you planning for that? Be kind of fun, right? Well, I won $1 million, this is what I'm going to do. Right? Have you won $1 million? No. What is the reaction equation? It's a plan. That's it. Specifies a plan. If I win $1 million, this happens. Okay? If these things actually react with each other, this is what I would expect to happen. Do they actually react with each other? That's a harder question. That question requires external information. That external information is known as the, not solubility, let's try, our activity series. Okay? The activity series is a way to describe the reactivity of different metals. The higher up on the activity series, the more active they become. Okay? The lower, the less active. Okay? Activity is always kind of a weird reference, so what we can say is the higher up, the more, let's say, more compound. The lower on the activity series, let's say less compound. That's a negative. I don't want to do that. I want another kind of positive, happy thing. Okay? What's the opposite of being in a compound? Okay? If you aren't married, you're single. So what's the opposite of being in a compound? You're single. You're by yourself. So the lower on the activity series, the more singular. Okay? Or by self. Okay? So whichever definition you want to use is fine, as long as you recognize it. If you want to do more compound, what would gold then be? It would be less compound. Okay? If I want to use the singular or by yourself rule, what would I say about lithium? It's less likely to be by itself. Okay, so let's go through and look at our equation. Okay, we already forgot what I was doing. Pb plus zinc sulfate. Okay? So the activity series gives me information about how these metals interact with their world. So I'm going to go through and look at them. I've got zinc right here, and I've got lead right here. So let's think about zinc. According to the series, what would zinc like to be? More in a compound. Where is zinc in a compound? On the right side of the equation. So zinc wants to be over here. Okay, lead. Let's look at lead. What does lead want to be, according to our series? Okay, more singular. Where's lead more singular? On the right-hand side of the equation. So when I mix zinc and lead together, what are they going to do? Does lead want to stay in a compound? Nope. It's saying, hell no, I hate people, get me out of here, and found somebody to substitute for them. So here you go. Talk to this person instead. I'm peacing out. Did the reaction happen? Yes. Okay. So we use the activity series to predict whether that reaction occurred. Okay. To give you the flip on this, if we look at the very, very bottom, I'm trying to do this one really fast. Copper and gold. Copper, gold. Which one do you want to look at first? Gold. Gold is what? Most singular. Where is gold most singular? On the left-hand side of the equation. We'll also go through and look at copper. What does copper want to be in comparison to gold? More compoundy. Where is copper in a compound? Does this reaction occur? No. We're already starting in our equation with exactly where they want to be. They don't want to exchange places. Okay? And as we kind of pack up, we'll talk about some kind of fun things. Let's compare lithium and gold. How many of you have worked with lithium before? Ooh, interesting. So not a lot of people have worked with lithium. How many of you have worked with gold before? Yeah, a couple people have worked with gold. Where have you worked with gold? In jewelry. Why do we not make jewelry out of lithium? It reacts with everything. It wants to form a compound. So if we made lithium jewelry and put that on, what happens? It reacts with your skin and melts your hand. That's not cool.
What's the thing that
Okay.
causes the green?
Nickel. I think it's nickel typically. The other one, gold. Where have we seen gold before?
On electronics.
Yeah, keep going.
Currency.
Currency. Why would we pick gold as our currency?
Because it stays.
It stays gold. Imagine Fort Knox and our currency was lithium. What does the terrorists have to attack Fort Knox with? With a water gun. And all they got to do is charge through Fort Knox throwing water balloons and water guns at all the lithium. What happens? All of the lithium that's a solid becomes an ion, dissolves into the water, and falls through the drain. What happened to our world currency? It is gone. Now we actually have to blow it up. And even then, if we blow it up, what happens? We still have chunks of gold that we could then put all back together. Right? So just kind of a neat observation. Chemistry gets us money.